Okay. So now we were seeing different things about genetic algorithm, and now we are here that okay, we have seen how we can select how the recombination things will go on. But the question is how the algorithm will terminate, because from the previous pictures we have seen that it will select, it will apply the recombination, new child will be produced, and then it will be the part of the population. Or you can say here, selection, recombination, and then again making the part of the population, and then again doing like that. So the question is when this algorithm will terminate. So here the answer of this question that there can be different approaches. There can be different approaches. One approach is that if the algorithm is running and you have found your solution, okay, then terminate the algorithm. Okay. And the other is the meeting the designer's criteria. So, for example, if you have developed the algorithm and you have your own thought, you can apply your thought there to terminate the algorithm. But again, that thought should be some kind of formula or something or some condition. Huh? So anyhow, this is also applicable on this universe. This universe is created by Allah Almighty, so everything is executing, huh? So evolution is going on, and then Allah knows that what is the criteria for the termination of this whole universe. So that's why that point is giving that sense more clearly. Okay, and then other option is that okay, you have designed the algorithm is running, and now you can leave it on the population that they will decide by themselves when they have to quit. Okay, so that can be another termination criteria. And then other one is, so you can leave it on the population. Either they can uh, terminate the algorithm before finding the solution or after finding the solution, because you are leaving this option to the population. And then another criteria to terminate is that if you will have suboptimal solution, and you can understand suboptimal, optimal is best possible solution, huh? Suboptimal is second best possible solution, huh? Second, third, fourth. So that is suboptimal solution. So if the genetic algorithm will run on some task, it will definitely give you the best possible solution. But if you don't have the time to wait for such a long time that you will get your optimal solution, then you want to quit now, and then what? You will get the suboptimal solution then. So this can also be a criteria. This can also be criteria that if you have reached on a suboptimal solution, okay, that solution is now achieved, so you can return from the module of the genetic algorithm. Okay, or you can how you can do something like that suboptimal solution. We are computing average, we are computing fitness values for each members in the population. Then you can do what? You can calculate the average fitness of the whole population by summing up all the fitness values and then divide it with the total number of members. You will get average, huh? So after finding that, after finding that average fitness, if you will see that the average value of the fitness that you are getting is closer to the maximum fitness value of the member which is available in the population. If your average is close to the maximum, you can introduce this condition in your algorithm that if average is close to the maximum, okay, suboptimal solution has been achieved. So terminate this genetic algorithm. So, so this is point number 4. Or you can have some other criteria to select suboptimal solution. But this is one strategy which is mentioned here. So when you are doing this, uh, this can be diversity, lack of diversity. This can be another issue, another situation in your genetic algorithm. We previously saw on some slide that if we have large population, then the population would be diverse, different people will with different fitness values, huh? But suppose if in the population of genetic algorithm, suppose if you don't have that diversity, if now you are lacking of diversity in your population, then what it means? It means that the people that you have in your population, they have the same values, huh? They don't have the different values. They don't have the diverse values, huh? Then in this situation, whatever member you will select, they will have the same values and they will produce the same children with the same fitness value, huh? And then you will not see too much betterment or too much good thing happening in in the members of your population due to the lack of diversity. This would be the situation. And I can say this thing now in a different way, that my members that would be in the population, that will converge on local maximum. I am saying the same thing. So for example, if you don't have, so this is, I can, just a minute. I want, okay, eraser. If you have state space like that, then here you have the diversity, huh? Some high, some, this is highest, and then in between, and then lowest. But if your space is like that, huh? Not too much difference, huh? So then what it means? It means that all the point, you can say, so all the local maximum are maybe the local minimum, they have almost same values. And then what? Your algorithm will give you either local maximum or local minimum. So say apply that same concept here. So then the members in our population, they will do what? They will converge on local maximum, which means they will give you the local maximum value as an answer. Normally converge means in Arabic, I think word is markuz is Arabic word. Markuz. Something like that. This is Arabic or not? Markaz, markuz. Markuz is not Arabic? Arabic? Yeah, I think. I think it is Arabic. Yeah. At different areas, you don't know actually. Why I'm saying that? Because these are the words coming from Arabic and that we normally study in different subjects, especially in physics. So from Markaz, it is Markuz. Markuz normally means that different things are coming and they are joining on the same point. Okay, that is the meaning of different things are coming and they are connecting on the same point. So then I can say these different things are Markuz on that point. Okay, this is Arabic. Anyhow, uh, so the members will converge on local maximum. And then what? You will not get some more better solution from this situation, okay? And if you are not going to get more better solution in this situation, then what is the solution? Just terminate. Terminate your algorithm then. Terminate your algorithm. And how you can find this situation? Again, this average fitness is close to the maximum fitness, huh? If you will use this condition, average fitness close to the maximum fitness, you can find this situation. You can find this situation that you will have the individuals in your population that are and their fitness scores are close to the maximum. So then what? You must have to terminate your algorithm. How you can do that? Either you can restart the algorithm, or you can use this formula, that is, if average is close to the maximum, okay, then terminate. Okay, now this is the genetic algorithm. Have a look on it just for understanding, and then we will see an example over it. So this is genetic algorithm. We are passing a population into it, and then we have a fitness function which will calculate the fitness value for the member. And then this algorithm will return an individual. It will return an individual. Individual means member of the population. So, and we have these two variables here. We are calling them population. Population is a set of individuals, and fitness function, that would be some formula, that would be some function that through which we can calculate the fitness of a member or individual. Okay, now we have the repeat until loop. So here we have the repeat until. Repeat. Here repeat means like while, huh? Like, but here maybe you have heard the do while loop, huh? So this is like do while, huh? Do, and this is the body of the loop, and here the condition is here actually. Okay. So now, initially we have a new population variable, new population. This is population, okay? And this is new population, two different variables, okay? And this new population, we are setting it to empty. So initially it is empty, and then we have the for loop starting from I is equal to 1 to the size of population, size of this population, not size of this, okay? This is empty, okay? This is empty. I is equal to 1 to the size of the population. If the size of the population is 10, this loop will go up to 10, 20, it will go up to the 20. And then, okay, for loop, and then we are selecting what? Random selection. So we are selecting something randomly from the population, from this population in which we will in which we have the individuals. We are selecting something from the population randomly by using this fitness function. Not using, you can say we are selecting something according to this, we are selecting something from the population randomly, and then we are calculating the fitness value of that member. This is what the meaning of this statement is. Hmm? And then, okay, when we are selecting some member from the population randomly, and then through this fitness function, we are calculating the score. And after that, that member will come here into this variable X with its fitness value. Huh? And then again, we are using random selection. Again, similar ways. So population and fitness function, and then it will return some member into this variable Y. And after that, we are using a module or function which has the name reproduce. We are passing these two variables into it, and this reproduce is written here. So we are calling this reproduce with these two members, X and Y. We are passing X and Y into it, and it will return us what? It will give us an individual. And what are we doing here? So here we are passing X and Y, which are what? Which are the individuals, which we selected here randomly. And then we are calculating the length of this first. This X is one member, so we are calculating the length of that bit string. Huh? So we are calculating the length. That length will come here in this N. Maybe, so the total length of the bit string available here for the individuals, the total length, suppose it is 10, huh? And here length of x is what? This n will contain 10. And then random number from 1 to 10, huh? So now we are selecting random number from 1 to 10. Suppose it is 7, huh? Then this 7 will come here in this C. Hmm? And then we have another statement, append. And then we are saying substring. Substring, which substring? So first we are considering this X. So we are saying, okay, X, consider X. Consider this X, the first one. From 1 to C. C is what? 7. C is what? 7. N is what? Suppose it is 10. This is the length of the string. And C is what? Randomly generated number from 1 to 10, that is C. So we are saying from 1 to C. So what this will do, it will extract the string from 1 to 7 from this X, okay? The first 7 bits will be extracted, okay? First 7 bits of the X string, okay? And then here we are comma and then substring. We are considering the other individual, which is y. Y from where? C plus 1, 7 plus 1, 8. From 8 to 10. So from 8 to 10, we are considering the bits from y. And then here we are doing what? We are doing the append. Append means you can say join them. So join this y after the x, that is called append. Huh? So you are appending these two strings together. And now the new string will be produced or not. So that new string will be returned here when this function will return individual. Huh? So that new string will be returned here in this variable child. And now we are checking here. We are checking some kind of probability here. Here you will have any formula of probability, okay? And through that formula, if you are getting small value of probability, small value normally means 0.1, 0.2, 0.3, huh? So if the probability is small, then we have this child, we are going to apply the mutate operation over this child. What is mutate? Mutation is what? Changing only one bit, okay? So in this child, so if we will have the bit string for this child, then we are going to change only one bit in that child, and then the bit string will be updated in the same, in the same child variable. In the same child variable. But here we can introduce some formula here. It is not written here in this algorithm. We will see what we will do. So here we can have different mechanism. Each person can have different mechanism. Here we can have some formula here, or how we can going to apply this mutate. And what we are saying here, if the probability would be that, we will say, okay, in the next example, we will say, if the probability would be that, then we are going to mutate, otherwise not. Okay, so mutation is, the condition for the mutation is there, which will work with this probability value. And then after this will happen. Add this. So now we have the child. Add this child to the new population. What is new population? This which is empty. So add this child to the new population. Okay, done. And then I will go again to this for loop. And then you will keep on doing that. And then again, I is equal to 2, you will select 2 members, and then you will apply the reproduce function over it. Then you will get the child, and then you will add the new child to the new population again. So in this way, in the new population, you will have 1, 2, 3, 4, 5. If in this population, you will have 10 individuals, then this loop will execute 10 times, and then this in this new population, you will have 10 children, huh? Because this loop has to execute up to the size of the population, huh? So if the size of the population is 10, then in this new population, you will have 10 new children. And only then this loop will terminate. Huh? And after that, you will add this new population of children to the population. So now the previous population is 10 plus this new 10. So 20. Eh? So you will have the 20 in the population, and then what? You are here. You are here until is the condition for this repeat, huh? For this loop. Until is the condition. What is that condition? We will keep on repeating that until we will get some individual fit enough. So this can be one condition. We can keep on executing this algorithm until one individual has, you can say, 80% of fitness. Okay. This is theoretically written here. So you can keep on repeating that until some individual is fit enough, and you can introduce some value for that fitness, maybe 80% or something, maybe 80. Or you have another condition for termination is or enough time has elapsed. Or you can say you have to execute this loop for 2 hours, for 4 hours, for 5 hours, for 20 days, for 20 months, huh? And something like that. You can introduce. So, and this repeat until loop will go on like that. And then finally, so if time is finished, then it will come out of this loop, huh? Or if 80% fitness value of individual has achieved, then this loop will end, and then you will come here and then return the best individual in the population. So and then you will see what is the best individual with the best fitness score. You will calculate through fitness function. You can calculate, and then you will return that individual. In this way, this algorithm is terminating. Understood or not? Hmm? It is easy. It is not that difficult. Now we will run that algorithm over this example. And this example is finding the maximum number between 0 and 31 by using the concept of bits. We will use that concept. So, but it is what? Finding the maximum of x, and x is what? X can take value between 0 and 31. So the maximum is what? 31 from here. 0, 1, 2, 3, 4 up to 31. What is the maximum number? 31. So now this algorithm, but we will run this algorithm, genetic algorithm over it. So for this, okay, we have 4 numbers, and then we are considering some starting numbers in the bit string form, and we will take these numbers randomly initially, okay? So here, for example, we have these 4 numbers. We have these 4 bit strings. So this is our starting population. Because when we studied that algorithm, we said that we can initialize the pool of the population randomly. Okay. So here it is initialized randomly with these bit strings. And then if you will calculate their actual number in decimal form, so then this is equal to 13. Huh? Similarly, this is equal to 24 if you will use the binary operation over it. And this is equal to, for example, this is 1, 2, 4, 16, 32. And this is 1, 2, 4, 8, 32. Okay. 1, 2, 4, 8. These are the positions. Huh? This is equal to 8. And similarly, this is equal to 19. And you all know how this is equal to How this bit string is equal to these numbers, you know that, huh? Because you studied fundamental of computing in the beginning, in the first semester or maybe. So the value of the value of the actual value of these thing is okay. This is x, and then here we are calculating some kind of uh, uh, f of x. We are calculating some value through this function, and what is that function? F of x is equal to x square. This is what we are basically going to make a formula for calculating the fitness of the individual. Okay, so but this is the first step. So f of x is equal to x square. If this is x, if these are the values of the x, then x square would be what? The square of it. Okay. So 13, take the square and you will have 169. Take the square, take the square, take the square, and you will have these values. Huh? Now, so the values that are here in this column, we are calling them what? X square, or we are giving a name to it, Fi. Okay. Fitness value, but not final fitness value. So this is something we are calling it Fi. Now we are going to calculate the fitness value through this formula, which is that what? Fi divided by F average. So offspring mean for child, okay? Offspring normally means child. So offspring number fitness. So Fi divided by F average. So this previous is Fi and F average is what? I have to calculate. So then what? Sum them up. Sum these all values. So these are the four values, and you will get what? You will get 1170. So now divide this 1170 by 4. You will get what? 293 maybe, huh? You can do that, huh? So 1170 divided by 4, you will have what? 293. Okay. 293. When you will divide this 1170 by 4, you will have this value. And what is the maximum from this column? Okay, that is also mentioned. This 576 is maximum. Huh? Now, how we are computing these values? Fi. Fi is this. I can remove all these now. So Fi is this value. Fi divided by F average. So now divide it with this value. And you will have this value. So 169 divided by the 293, you will have 0.58. Similarly, 576 divided by this value, you will have 1.97. Similarly, 64 divided by 293, you will have this value. Similarly, 361 divided by this 293, you will have this value. So you are getting now, this is the fitness value you are getting from the previous step by using this formula, Fi divided by F average. And then again, the sum and the average of this column and the maximum is written here, huh? The sum, average, and maximum. Now, if you will make the value round, so 0.58 rounded to 1, 1.97 rounded. If you will make it round, then it would be 2. Similarly, this would be 0. This would be what? 1. By round, mathematics round, if you have 5 and higher value, 0.5 and higher, so after applying that round operation, you will have this one. Okay, the sum, the average, and the maximum of this column is written here. Moving next. So again, I am writing all these bit string again here. So here we are writing all those bit strings. We have only, up to this point, we have only calculated the fitness function. We have not selected anything, and we have not applied the recombination process of the genetic algorithm over them yet. We have only calculated the fitness function. So that's why I am repeating all these. I am repeating all these bits again. And now we are going to apply the recombination process, selection and recombination. So here, for these bit string, we are selecting the partners. Which partners which are going to mate? We are going to select these partners randomly. So, and here we are saying, okay, this is the single crossover point. Okay, and we are saying that this partner, this member, which is member number one, it has the partner two, which means this one, second one, huh? And this then two will have the member what partner one. So they both will mate with each other. They will do the recombination process will be applied on them. And for this, the partner is four. And for this, if for this, this is third, huh? And if the partner of third is four, then the third will have three. Then it means they will do the mating. Okay, and for here, we are selecting this point as a single crossover point. So crossover point for the operation crossover, we are selecting it also randomly. You can select after 2, after 4, whatever. But for this, we are selecting it randomly. And it is first bit, second, third, fourth. So after the fourth bit, we are selecting the crossover point for these two members, number 4. And then if it is a single crossover point, then after number 4, we can do what? We can swap the tails. So we can move this tail to here, and then we can move this tail to here. This is what we studied in single crossover point. So then what? This 011 is the same, but we are changing this tail to here. And similarly for this sequence is same, and we are changing this tail to here. Similarly, you can do the same operation for this, but here the crossover point is 2, which means this is the crossover point. And then you can swap the tails, and you will get these bit string. And again, what these bit string are equal to these decimal values, if you will calculate. And then again, do the square. This is the square. And then again, okay, this is the square. This is the sum them up, take the average by using those previous methods, huh? By using those previous methods. Calculate all. Sum them up, divided with 4, and then you will get the average. And the maximum also, this one. Now you can calculate the fitness for that. And here the fitness, for this member, the fitness is 0.32 by using the same formula, previous formula. Here the fitness is 1.42. Here the fitness is 42, and here the fitness is 58. Now round it. If you will make it round, you will get 0. Here, if you will round, 1, 0, 1. So these are the rounded values, which we are not using. We are selecting randomly. But I can say to use these values. Select the highest, something like that. Now I will take this. This is the population, the modified population. And I reproduce the values here, copy pasted the values here. And then random partner. For this one, the 3. So and then this for third, it is 1. So now these are the partners. And the random crossover point we selected third, which means after this, after third. This is the third. After third point, you can swap. So then what? 0, 11, and then 11. This is this bit string you will achieve. And then here, 0, 1, 0, which is here, and swap it with this, and you will have this one, which is equal to, if you will convert now, 15, 16, 8, 25. So we have reached up to 25, huh? But where we want to reach? 31. 31. And if you will take this again here, and if for the first you have the second, and then for the second, so again, we are going to do something that. And the crossover point is what? 1. 1 means this is the point now. And then after 0, I will get this whole, in the next, I will get this whole, huh? If you will swap. If you will swap, because we are swapping 1 and the third one. So 0 and swap after this 0, what is the crossover point? Sorry. So now in the next, in this step here, we are selecting what? For first, we are selecting second. So then we are going to apply something between that. And the crossover point is also 1, which means this and also this, not third one, okay? And then with this 0, and you will have all these zeros, and here you can see the bits rate. Similarly, 1 and then all ones, you are seeing this one. And similarly, you can do the things here. And this is equal to what? This is equal to 31. And when you reached, you can go out of this algorithm. But there is an interesting point. But when we were here in this previous step, I'm not talking about this step. I'm not talking about this. When we were here in this step, we can apply mutation over here because we only have to change one bit and then we will get 31. Huh? In the second last step here, in the population, in the second last step here in the population, we have some substring on which you can apply the mutation, and then you can get the 31 within this step. And how you can, for example, how you can do this? If you have this probability for the if in the algorithm we said if we have small random probability, then we can mutate. So for example, if our small random probability value is, if we will assume that this would be the value 0.001, then what it means? It means basically 1 divided by 1000. What it means? That within 1000 bits, you can consider only one bit string to mutate. Okay. So for example, here in this example, yeah, I know that time is finished. I'm just finishing. After that, the topic is changing. So here we have 5 bit strings, and in each bit we have 5 bits. So if I multiply 5 with 4, I have 5 sequences, and each sequence has 5 bits. So 5 multiplied by 4, and if I will consider this probability, and if I will multiply them, when you will multiply them, it would be 0.02. And if you will convert it into fraction, it means 2 by 100, which means within 100 sequences, you can apply mutation 2 times. And here, when I was executing this algorithm from the start, just 1 or 2 minutes. I am finishing just this topic. Just, yeah, just finishing.
Oh my God.
Just 1 minute. No, just one, maybe, yeah, just 1 minute. I'm just coming after you. Okay, so it means that from this 100 bits, you can mutate two sequences. And up to this point, I have not used this option yet. So here I can use, because here, this is the starting, and here I have 20 bits. From first 100, I can apply mutation 2 times. I have not applied here. And then here, I have got the second generation, 20 plus 20, 40. And now this is 30, 40 plus 20, 60. So within these 60, I can apply because according to this formula, I can apply mutation 2 times. So you can apply mutation here and you can get your 31 finally. So now I am sorry, I'm stopping here.